Hello everyone. In the last video, we have seen what is gradient descent and how to use gradient descent to solve linear regression with single variable. Now let's look at the real world examples where there won't be a single variable but a set of variables and how to solve that problem using gradient descent. So this is an example of linear regression with a single variable where we have seen the size of the house determining the price of the house. So we have represented the hypothesis as θ0 plus θ1x. Since we have a single variable size of the house, our hypothesis representation is like this. Now, if we have multiple variables, so we are given not only the size of the house, but number of bedrooms and age of the house. And these will together determine the price of the house. Then our hypothesis will be a function of θ0, θ1, θ2, θ3, and x1, x2, x3, where thetas are the parameters and x represent the variables. And also you can see, we can simply put x0 as well here, so that that equation will look complete, and x0 we can initialize as 1. So in that way, we can represent the hypothesis in a much better manner. And I want to give an example by substituting the values of parameters that can fit this training data. So if we consider 100K to be the base price of any house, so θ0 if you put as 100K, 100 plus 0.01 times size of the house plus 1 times number of bedrooms minus 0.1 times age of the house, because with age the price of the house will go down, because a 30-year or a 40-year-old house doesn't hold any value. So we have to subtract the age of the house. So the parameters can be negative as well. They can be positive as well, they can be negative as well, and they can be small as well, and they can be big as well. Okay, so our hypothesis, let's go into the next slide. As x0, I already told it will be initialized to 1. So our hypothesis can be represented by in this manner. Now, writing long equations like this every time we have multiple variables will make it look very large, as well as it will not help us go into the crux of the problem. So instead of representing the hypothesis in this manner, we can try representing the hypothesis in a matrix format. So the parameters θ0, θ1, θ2, θ3, or if you have till θn, they can be represented by a vector format. So now you can put a single theta and represent all the parameters in the vector format. And similarly, all the variables you can represent in a vector format. Since x0 is 1, so it will still like the old hypothesis. Now, if you're aware of matrix multiplication, you can see if we take the transpose of theta and multiply it with x, we get the hypothesis. So our hypothesis can be represented in a simple manner, like h of x equal to theta transpose x. Now let's go back to see how the gradient descent can help us in solving this multivariate problem as well. So we already saw this gradient descent for single variable, where θ0 or theta 1, you are subtracting the gradient with respect to the same parameter itself and multiplying with alpha, which is the learning rate. And if we derive the partial derivative with respect to that parameter, we get equations like this. And we can see one commonality here where we are multiplying this part with the variable xi. This corresponds to the feature. And here as well, for theta 0 also, since we consider the feature parameter, feature variable to be 1, so you can also put dot times x0 here, and that corresponds, that dot times xi, I'm sorry, where xi is all ones. So for all the training samples. So in this manner, we can see there is a common thread to these equations where we are multiplying with this set of equation here with xi, and let's put a j as well here, because the j corresponds to that particular feature. And here I represents the ith training sample. So this equation can be combined together. And so, okay, this slide I'll come back later. So repeat until convergence, theta j, where j corresponds to the jth feature. The parameter is subtracted by alpha times its gradient. And if we calculate the gradient or the cost function partial derivative, we get an equation like this, which is multiplied by xi, where I is our training sample, and it's a subscript with j, where j is the feature variable. And we have to simultaneously update all the theta j. So this rule applies if you have single variable or multivariable variable as well. So it's as if all the theta j are being updated in parallel. And we have to continue doing this until convergence. Convergence is nothing but this theta j on the left hand side becomes almost equivalent to this theta j on the right hand side. So it means your gradient, whatever the gradient you are looking at here, it almost reaches near to 0th value. And how we are deriving this xj for a given cost function. So not xj, for this particular equation for a given cost function, this is available in this slide. So if you are aware of the calculus, you can look at the derivation, and this will ultimately result in h of x minus y times xj, which is there in our next slide. Okay, so that's it for today's video, and thanks for watching the videos. If you like these videos, please like, share, and subscribe. I'll be doing more videos in this. Thank you.